I'm Florian, and in this presentation I'm going to tell you about some of my recent work on a new approach and transformation to remove more redundant range checks in LLVM. Let's start by taking a look at the motivation behind this work. Our main focus for the project was to increase the number of complex range checks that LLVM can remove. We are interested in removing both integer and pointer range checks in particular. But the approach is not really specific to range checks in any way and generalizes well for complex conditions and checks in general. On the slide, there is a reduced code example from a bug report with a range check that cannot be removed at the moment. The function takes a vector and an end index as arguments. It then iterates and sums up all the elements up to an end index. Note that the add accessor is used in the loop to access the elements in the vector, and this accessor first checks if the index is in range. If the index is not in range, it will abort the program. So here we have an integer range check in the loop, and now let's take a look at the information available in the function to see if we can remove this range check. First, we know that the end index is in range. Next, we also know that the loop index I ranges from 0 to end. And we also know that the add call checks if the passed-in index is less than data.size. Now, if we combine the first two pieces of information, we can remove the range check. So the key to removing range checks here is the ability to effectively reason about multiple conditions together. So we need to combine information from multiple conditions to remove the range check. Now let's switch from C++ to LLVM IR. On the slide, we have an LLVM IR function with three conditions that are chained together through branches. Please keep in mind that the example is intentionally kept simple, so we can use it as a running example throughout the presentation. But the approach is able to deal with much more complex cases, both in terms of the number of conditions we have to combine information from, as well as the complexity of the conditions themselves. But even for this simple example, LLVM is not able to simplify this at the moment. Now let's take a closer look at the function. We have the following information. We have two conditions, a less than equal b and b less than equal c, which both dominate the then2 block, where we have a third condition that checks whether a is less than equal c. This condition is implied by the dominating conditions, and ideally we would simplify it to true. Before introducing the new pass, I'd like to take a quick look at the current state in LLVM and some of the possible shortcomings that a new pass ideally should address. At the moment, most of the reasoning about symbolic conditions in LLVM is somewhat ad hoc. With that, I mean first that in multiple places, LLVM is trying to discover facts to use for reasoning on demand, so by looking backwards in the CFG at the predecessors. This means the same parts of the CFG are traversed repeatedly, and we need a tight limit on the number of steps we look backwards to keep compile time manageable. This in turn means it's easy to miss important conditions, which we could use to simplify conditions. When it comes to the reasoning itself, there is a reliance on pattern-based simplification, which means a lot of code would be required to combine information from multiple conditions, and that does not really generalize very well. While it would be possible to simplify the code in the running example where we needed to combine information from two conditions using the existing infrastructure, it would be very difficult to do so in a way that generalizes well to handle an arbitrary number of conditions. So for those reasons, we started exploring a new path and a new approach to remove range checks more effectively. Let's switch gears now and take a look at this new path. It consists of the following key ingredients. First, we need an efficient way to collect known facts from conditions in a function. To do so, we will iterate over a function in an order that allows us to keep track of the scope of conditions in the function. As we go along, we take a look at conditions in the function, and the LLVM IR expressions are then decomposed into linear inequalities, which allows us to reason about them later on. This is then combined with a general mechanism to reason about the known facts we have available. To do so, we maintain a system of linear inequalities where we add facts we discover and we remove them once they go out of scope. This allows us to reason about our information automatically by checking satisfiability of a system of linear inequalities. This is something that can be done automatically, for example by using a technique called Fourier-Motzkin elimination. This is what we are using in the initial implementation. When it comes to validation of the transformation, the state of the transformation can also be used to help with verifying the transformation itself. But more about that later. Now let's take a closer look at how we can collect the known facts in a function. On the slide, we again have our running example and the dominator tree for the function. We will use the fact that a condition holds in all blocks dominated by the true successor of a conditional branch. And then the depth-first search in and out numbers of the dominator tree represent the range of nodes dominated by a given block, and this can be used to represent the scope of our conditions. The in number of this numbering scheme is assigned the first time a node is visited in the depth-first traversal of the dominator tree. The out number is assigned once all children have been visited. For the tree on the slide, we get the following numbers. Now we can map the conditions in the function to the DFS numbers to create a work list for our function. So we know when we enter the then1 block a less than equal b holds, so we'll add this condition with the corresponding depth-first search numbers. Next, we also add the then1 block itself to the work list, so we can simplify it using the information in the current scope. Similarly, when the then2 block is entered, we know that b is less than equal c, so we'll add it to the work list. And we'll also add the then2 block and the exit block. Now we have our work list, and for each entry we process, we will do the following. If it's a condition, we add the current condition to the set of known facts. And we will also remove all conditions with out numbers less than the current in number from the set of our known facts, because they are out of scope now. So for the work list for our example, we'll start processing it and we'll first add the condition a less than equal b to the set of our known facts. Then we will process the then1 block and try to simplify conditions in the block using the information that's in scope at the moment. We will continue processing the work list, and when we finally reach the last entry, we need to remove all conditions we added so far, because the out numbers are now less than the in number of the exit block. So they are out of scope now because they don't dominate the exit block anymore. We now know how to iterate over the function while maintaining the set of known facts that hold at any given point in the program. Next, we need to reason about the facts. To do so, we need a data structure that allows us to, on one hand, add and remove known facts as we go along in our traversal, and the data structure also needs to allow us to reason about the known facts we collected. To do that, we use a system of linear inequalities. In this system, each condition is a row in this system. And then we can use Fourier-Motzkin elimination to check whether the system is satisfiable or not automatically. Note that there are other algorithms that can be used to check this system, which could be implemented as extensions in the future. So how does this now work for our running example? Through our traversal, we will add a less than equal b to the system when we enter the then1 block. Then we will also add b less than equal c to the set of our known facts when entering the then2 block. In the then2 block, we have the condition a less than equal c. And this is what we want to simplify. To do so, we need to check whether the system containing our known facts implies the condition. To do so, we can add the negated condition to our set of known facts. This looks something like this on the slide. Now, if the resulting system shown on the slide is unsatisfiable, this means there can be no assignment to the variables that makes a less than equal c false. Hence, the condition must be true and can be simplified. In this case, the resulting system is not satisfiable, and we can replace the condition with true. It is also possible to support comparisons with more complex IR expressions by converting the expressions themselves to inequalities to include the arithmetic operations. For example, if we have an add feeding an unsigned compare, the add can be included in the linear inequality. So the expression on the slide can be decomposed to the constraint a plus b less than equal c. So we can include the add directly in the inequality. But note that we have to be careful when decomposing arithmetic expressions, because we can only decompose operations that are guaranteed to not wrap. In this case, we need to be careful. So for adds and operators, we need to carefully check the overflow flags that are involved in the operations. In some cases, additional conditions must hold for expressions not to wrap. Consider an inbounds gap as on the slide. It won't wrap in the unsigned sense if the index is signed positive. So we can convert it to a linear inequality as shown on the slide, but only if the offset is signed positive. This is a precondition, and we can of course check it against the set of known facts we maintain, like any other condition in the program. When it comes to reasoning about loops, we may need to combine facts from multiple incoming edges. So for example, if you consider the loop preheader, we might need to combine information. If you consider the loop header, we might need to combine information from the loop preheader and the loop latches. This would require merging systems of linear inequalities, which is more complicated both in terms of implementation and computational complexity than just maintaining a single system of linear inequalities as we iterate over the function with our dominance-based approach. But when it comes to loops and conditions involving loops, we're mostly interested in information about loop induction variables. To deal with loop induction variables, we can use existing analysis like scalar evolution to derive facts about loop induction variables and then inject this information in form of conditions into our work list. And this allows us to handle loops with loop induction variables without having to merge multiple systems of linear inequalities. And for most range checks we encounter, this works very, very well. Now let's briefly talk about validation of the transformation. We're interested in validating the transformation because the LLVM semantics related to overflows in both integer and pointer arithmetic the transformation deals with can be very subtle, and it's easy to get edge cases wrong. We also need to support pointer arithmetic, which may overflow. So the transformation also supports get element pointers that are not in bounds. To support those, we need to prove that the computation cannot overflow, and we need to do that separately first. To make sure the transformation handles all those cases correctly, we used LLVM to verify correctness of the IR transformation from the start. Now, one thing to note is that verifying large LLVM IR functions can become unfeasible due to the high compute cost required as LLVM IR functions get larger. But the question is, could we still verify range check eliminations performed on large-scale programs? So basically, can we verify that the range checks removed are correct for an end-to-end compilation of a real-world C and C++ program? And the answer to that question is yes, there is something we can do. If you think back a couple of slides, we have the system of linear inequalities, which contains the set of known facts we used for each transformation. Now we can use this system to construct reproducer functions by materializing inequalities back into LLVM IR. For our running example where we simplified a less than equal c based on a less than equal b and b less than equal c, we can construct a reproducer function that looks something like this. We have our known facts chained together through conditional branches, and it returns the condition we simplified. Those extracted reproducers are minimal in that they only contain the relevant instructions and facts we used for reasoning, and no other instructions like unrelated function calls or unrelated memory operations that may increase the complexity of the verification. And this now can be used to audit each transformation using LLVM for an end-to-end compilation, because we can translate a large-scale C++ project and extract the reproducers for each range check transformation, which then can be verified later. To wrap up, let me share some initial results. The new transformation already fixes a few reported bugs related to redundant bound checks reported in the LLVM backtracker and linked below. It also is able to remove 35% more pointer bounds checks instructions emitted by a downstream frontend we use this transformation for. Compile time increase is notable but not excessive. And the transformation is able to simplify up to 5,500 more conditions across back and multi-source with O3. Of course, there are a couple of limitations to keep in mind with this approach. At the moment, we can only handle linear expressions, so we can't support modulo or shift operations. And we require non-wrapping expressions to decompose them. So to work most effectively, we need operators with the correct overflow flags. And of course, there's also potential for future work. On one hand, there's potential to improve the compile time even further by tuning the solving part of the implementation, which I didn't spend much time on so far. And also, it would be interesting to investigate which frontends would benefit most from this transformation. For example, because they emit a large number of pointer or integer range checks, and then work towards enabling the pass there by default. That brings me to the end of the presentation, and I'm now ready to take your questions. Thank you.
Oh, folks, we're here to take your questions. So first, thank you, Florian, for your presentation. It's very interesting to see this unfold. We have one question to start. From Ian Rogers, who asks, this approach is reminiscent of ABCD, which struggled due to sign types and underflow. Decomposing a loop into 3 loops, underflow, node check, and overflow works well. Is this approach tried as well?
So I'm not entirely sure what what the pass or transformation was that's mentioned in the question. But yeah, I mean, the initial implementation focuses on cases where we can prove without any other transformations that we don't have overflows for expressions. I mean, as further extension, we could consider transformations that duplicates code and with multiple versions where we have multiple versions. So one for not overflowing and support more cases like that. But I think it's not on the roadmap for now.
Thank you. And then we have another question from Jacob Kuderski, who asks, does this approach intersect with traditional abstract interpretation techniques?
Yes, I mean, it's in a way, it's a cheap person's approach to abstract interpretation because we only work on a dominance-based approach where we forward propagate all the information we have. And what we don't do at the moment, which you would have, I think, in more classic abstract interpretation, is where you merge the states when control flow converges again. And this is something that this approach doesn't do at the moment.
Thank you, Florian. So we're still taking questions from the audience here. We have a few more minutes. We have Philip Reams asking, is this pass available upstream? If not, plans to contribute?
Yes, so an initial version is available upstream, and I have a bunch of follow-up patches that implement some of the more advanced features that I mentioned in this talk, and also to generate the results that I have on a branch that's available on like my LLVM fork. But after giving this presentation and after possibly soliciting more feedback from the upstream community, I'll be happy to push the rest of the changes upstream as well. I think one thing is that the main motivation, I mean, for regular C++ code, it's not extremely helpful, or it's more focused on languages where you have more range checks in general that are generated. So what I'm looking for is other front ends that would benefit, that are upstream, for really to drive this work in upstream.
Thank you. And then our next question, can users inject facts, for instance, using built-in assume?
Yes, so this transformation already uses this trick to inject conditions at certain points in the program, for example, from other sources. One example mentioned in the presentation is information about loop induction variables from SCEF. And so if you have other sources like built-ins or other constructs that you want to inject information or conditions from, then this is also possible, yeah.
Awesome. So next question that we have is it reasonable to introduce runtime checks, for instance, overflow checks, in order to enable the analysis and hopefully remove other checks?
I guess it is possible, but it makes things much more difficult because you have to now consider the cost of the runtime checks you introduce and consider the trade-off with how many additional how many additional conditions you can remove. And at the moment, the pass itself doesn't consider any costs because it just simplifies conditions that are redundant. So this would be a more complex extension, I think.
Thank you. All right, we have a few seconds left. I'm not sure we'll have time for it, but are these range checks always compiler generated? If not, are there opportunities to fix source code?
I mean, the initial example in C++ is not really compiler generated, right? It's from a user function call. Yeah.
Okay, well, that's it, folks. Thanks a lot for watching. Thank you, Florian, for your talk.
Thanks. Bye-bye.
Have a great day, everyone.